All right, so let's keep going with patterns and functions here, but now we're going to look at nonlinear functions, and I'll start off with a quick introduction to what those are, and we'll do a couple examples. So nonlinear functions are really exactly what they sound like. They're functions that do not create a linear pattern. So here are two examples of linear functions, although a preview for down the road, this one right here is officially not a function because it is a vertical line. It doesn't fall in the category of functions. But this second one right here is definitely a linear function. So in contrast, we will be looking at nonlinear functions today, essentially functions that have curves to them. So this is an example of an exponential function. This is an example of an absolute value function. And this is an example of a quadratic function, which creates a parabola. Okay. The absolute value function, you can see, is composed of two rays, or two half lines. So in some ways it has a linear component to it, but it is a nonlinear function. So one of the first challenges that we'll have to work with in this topic is to figure out, is a pattern linear or is it nonlinear? The easiest, although maybe a little more time-consuming way of doing it, is to just plot the points. So I want to do that with these two data sets, and then I will show you a little bit of an easier way of determining if things are linear or nonlinear. So let's work with the left-hand one first. Over 0 up 1, over 2 up 7, over 3 up 10, over 4 up 13. Looks like we missed a point too, so let's go back and snag that. I missed the 1, 4 point. And then the over 5 up 16. Definitely looks linear to me. Okay, so we can draw a line through these points, and it seems like it hits them all. So I'm going to call this a linear function. Let's try the next one. And let's contrast it and see what we get. So we have an over 0 up 3, about there, over 1 up 4, so a little bit higher, over 2 up 7, over 3 up 12. Do you see how we're starting to track higher here? So each time we go over 1, it seems like we're going up by more. So this is looking non-linear to me. Over 5 up 28. Yeah, it definitely looks non-linear to me. It looks like it could be a parabola. And we could try to sketch in the curve that tracks these points. But it does look, it's definitely a nonlinear function. So this is nonlinear. Easy way to tell it just from the table, though, without needing to graph, is just look at the change. Okay, so this is plus 3 each time, and that stays consistent. So that makes it this consistent change makes it a linear pattern. This change is not consistent. Plus 9 there, okay? So what we're seeing here, the fact that the change varies makes it a nonlinear pattern. So it's steepening. You can see that the change is increasing. Okay? So that's evidence that it's a nonlinear pattern. And let's do an example with this tile problem here, this pattern problem, and we'll fill in the table and we will graph the points, and I'm going to leave it as a challenge for you to try to come up with the rule for these points for this function. Okay, so we could have step number, and here it looks like we're tracking number of squares. We can count those, and those will be our x and y variables, or our independent and dependent variables as well. And let's wait to label the scale on my axes until we see what the numbers are in the table. So step number 1, 2, and 3. So this is 1, 2, and 3. And you'll see that I always like to leave a row for step 0. Okay. And if it's a clear pattern, we might try to continue in our heads what the next few rows are. But step 1 definitely has 3 squares. Looks like step 2 has 6. And it looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we can definitely tell that it's nonlinear because the change is changing, okay? So it's not a consistent change. And it looks like the change is changing, though, in a pattern. So we might be able to continue that pattern. That's what I would hypothesize. To really confirm this, I would actually draw out the next few figure numbers with the actual tiles. Plus 2, so that would be a 1. Let's plot those points. So we need our steps to go from 1 to 2 to 3 to 4 to 5. And let's get up to about 21. I will go up by, I can go up by ones here, but just every other one. 6, 8, 10, 12, 14. I won't go all the way to 21, but that's okay. So over 0 we have a 1. Over 1 we have a 3. 2, 6. It looks like it, just from the graph, it looks like it could be linear at this point right now, but let's see what happens. It looks like it's, yep, it's steepening for sure. 4, 15. Okay, and so we will try to sketch in. This is actually going to be a quadratic pattern. It's a parabola. If we were to continue it further to the left, it would eventually track back up, although that's weird to think about for a tile pattern. How could you have negative step numbers and increasing tiles as you go negative? But this is definitely a nonlinear pattern. So once again, I'll leave it to you to try to come up with an equation and see if you can predict how many tiles there might be for, say, step 100 using an equation. That's a good place to stop right there.